Scientists thought this was impossible until monitoring this space phenomenon revealed new data. Something out there is not behaving the way it should. Not according to the equations that have guided us for generations, not according to the models that helped us map the stars, and certainly not according to the confidence we built while observing a universe that seemed orderly and predictable. For a long time, we believed that the cosmos, as vast and mysterious as it is, still played by rules we could understand. Every signal, every movement, every fluctuation had a reason, a cause, a place within the logic of reality. But then, something appeared. It did not announce itself with a dramatic explosion or a visible spectacle. It emerged quietly, almost hidden within the noise of data, like a whisper buried beneath the static of the universe. At first, no one paid attention. Instruments detect anomalies all the time. Most of them mean nothing. Most of them disappear when you look closer. But this one did not disappear. It persisted. It returned. And with each observation, it carried a message that no one was prepared to hear. What happens when reality refuses to follow its own rules? That is the question scientists are now facing. Because what they found was not just unusual, it was not just rare, it was something that should not exist at all. Something that forces us to confront a possibility we often avoid. The possibility that our understanding of the universe is not just incomplete, but fundamentally flawed in ways we are only beginning to see. And if that is true, then this is not just a discovery. This is the beginning of a shift, a moment where the universe stops being something we observe and becomes something that challenges us back. So stay with me, because what we are about to explore is not just a phenomenon in space. It is a crack in the story we have been telling ourselves about reality, the signal that should not exist. Far beyond the reach of our solar system, in a region of space where silence is expected and nothing remarkable should happen, something sent a signal. It was not a steady transmission, not a rhythmic pulse like the ones we have cataloged for decades. It arrived as a sudden burst of energy, brief, irregular, and almost easy to ignore. For a moment, it looked like noise, a fluctuation buried inside a vast ocean of cosmic static, the kind of thing scientists are trained to discard without hesitation. But this one refused to disappear. The instruments recorded it with precision. The data was clean. There were no obvious signs of interference. No nearby sources that could explain it, no technical failure that could be blamed. Still, skepticism prevailed. Because in science, doubt is not a weakness. It is a safeguard. And so the signal was questioned, tested, reanalyzed, and challenged from every possible angle. The assumption was simple. There had to be an explanation that fit within the known boundaries of physics. Then it happened again. Another burst, similar, but not identical. It did not follow a predictable rhythm. Yet, it was not random. There was something hidden in its timing, something subtle in its structure, a pattern that seemed to shift just enough to avoid being easily defined. This is where the atmosphere changed. What had once been dismissed as an isolated anomaly began to take shape as a recurring event. And with each new detection, the possibility that this was real became harder to deny. Now, imagine the weight of that realization. For generations, scientists have mapped the universe with increasing accuracy. They have identified signals from pulsars spinning with clock-like precision, detected gravitational waves from colliding black holes, and observed the faint glow of radiation left over from the birth of the cosmos. Each discovery reinforced a deeper truth. The universe, no matter how vast, behaves according to laws we can understand. It may be complex, but it is not chaotic without reason. This signal did not belong to that story. Its energy profile did not match known phenomena. Its duration defied expectations. Its origin appeared distant, yet the clarity of the detection suggested something far more structured than a random cosmic event. It was as if something had emerged from the darkness not to be seen, but to be noticed. And the more attention it received, the more it resisted explanation. At this point, the question was no longer whether the signal was real. The question became far more unsettling. What kind of process could produce something like this? Attempts were made to classify it. Comparisons were drawn with known astrophysical sources. Models were adjusted, parameters stretched, assumptions tested. Each time, the same conclusion emerged. It did not fit. It refused to align with the frameworks that had successfully explained so much of the universe before. And that is when a quiet tension began to spread through the scientific community. Because when data refuses to agree with theory, something has to give. Either the signal is misunderstood or the theory is incomplete. And if the theory is incomplete, then the implications extend far beyond a single anomaly. It means there are aspects of reality we have not yet grasped, mechanisms operating in the universe that remain hidden from our current understanding, possibilities that challenge the very foundation of how we interpret space, time, and energy. This is where curiosity transforms into something deeper, not fear, but a kind of profound awareness. The realization that the universe is not just a system to be studied, but a mystery that continues to unfold in ways we cannot predict. The signal did not ask for attention, it demanded it. And as more observatories turned their gaze toward its origin, as more data began to accumulate, one thing became undeniable. This was not an isolated event. It was the beginning of something much larger, something that would force scientists to confront a possibility they had long kept at the edge of their thinking. The possibility that the universe does not always follow the rules we believe define it. And if that is true, then this signal is not just a discovery. It is a warning, a quiet indication that reality may be more complex, more dynamic, and far less predictable than we ever imagined. What seemed like a single anomaly was about to become something far more difficult to ignore. When the universe seemed predictable. There was a time when the universe felt understandable. Not simple, not small, but governed by principles so consistent that they gave us confidence. We could look at the motion of distant galaxies, measure the light from ancient stars, and trust that behind every observation there was an order waiting to be revealed. The cosmos, in all its vastness, followed patterns, and those patterns could be translated into equations that held true across unimaginable distances. This sense of predictability did not come easily. It was built over centuries of observation, correction, and discovery. Each generation refined what the previous one had learned, turning uncertainty into structure. Gravity explained the motion of planets. Relativity reshaped our understanding of space and time. Quantum mechanics opened a window into the smallest scales of existence. Piece by piece, reality became something we could model, test, and predict with astonishing accuracy. There is a quiet power in that kind of understanding, because when you can predict how the universe behaves, you begin to feel a sense of control. Not control over the cosmos itself, but over your ability to interpret it. You can anticipate outcomes. You can simulate events that have not yet happened. You can look at a signal from deep space and recognize it instantly, placing it within a category that makes sense. A pulsar rotates with precision. A supernova follows a known progression. Even the chaotic dance of galaxies obeys underlying laws. And so, a narrative took shape. The idea that while the universe may still hold mysteries, those mysteries exist within a framework we are steadily uncovering. That nothing truly exists outside the reach of explanation, only beyond our current level of detail. It is a reassuring thought. It suggests that given enough time, enough data, and enough refinement, every anomaly will eventually find its place within the system. But this confidence carries a hidden assumption. It assumes that the rules we have discovered are complete enough to describe everything that exists, that the unknown is simply an extension of the known, waiting to be revealed. And for a long time, that assumption worked. Every new discovery, no matter how surprising, eventually aligned with the broader structure of physics. Even the most extreme phenomena, from black holes to cosmic expansion, found their place within the boundaries of theory, until something appeared that did not. Because the signal we just explored did not behave like an extension of what we already understood. It did not refine the model, it challenged it. And that is a very different kind of moment in science. It is the difference between solving a puzzle and realizing that the puzzle itself may be incomplete. Imagine standing on a map you have trusted your entire life, only to discover that an entire region of reality was never included. Not because it was hidden, but because the map itself was never designed to account for it. That is the kind of shift we are facing now. A shift that forces us to reconsider not just a single phenomenon, but the assumptions that made us feel certain in the first place. This is where the story changes direction. Because when the universe stops behaving predictably, it does not just introduce confusion, it introduces possibility. The kind of possibility that can expand our understanding in ways we never anticipated. But before that expansion can happen, there is always a moment of resistance. A moment where the mind tries to hold on to the familiar, even as the evidence begins to pull it away. And that moment has already begun. Because if the universe was truly as predictable as we believed, then the signal would not exist. It would have been explained, categorized, and filed away like countless observations before it. But it was not. It remained outside the system, quietly insisting that something was missing. The question now is not whether the universe is predictable. The question is how long it has been giving us signs that it is not. And if this is not the first sign, then what we are about to uncover may have been hiding in plain sight all along. The first glitch in reality. Long before the signal demanded attention, there was a moment so small that it almost disappeared into routine analysis. A deviation in the data, a fluctuation that did not align perfectly with expectations. It did not trigger alarms. It did not disrupt the flow of observation. It simply existed, quietly misaligned with what should have been there. And because science is built on patterns, anything that breaks a pattern is noticed, even if it is not immediately understood. At first, it was treated as background noise. Every instrument that scans the universe collects far more data than it can use. Hidden within that data are imperfections, distortions, and artifacts created by the environment, by the instruments themselves, or by processes we already understand. Scientists are trained to filter these out, to separate signal from noise, to recognize what matters and what does not. And this anomaly, in its earliest form, looked like something that did not matter. But something about it lingered. It was too precise to be random, yet too inconsistent to be classified. It appeared at the edge of detection, then vanished. When researchers revisited the data, it was still there, unchanged, waiting to be interpreted. This is the kind of moment that does not create excitement at first. It creates hesitation. Because acknowledging something you cannot explain means stepping into uncertainty, and uncertainty is where assumptions begin to unravel. So the anomaly was tested. Data sets were compared. Instruments were recalibrated. External sources of interference were ruled out one by one. Each step was designed to eliminate the possibility that this was a mistake. And with every test that failed to remove it, the anomaly became more real. Not louder, not more obvious, but more persistent, like a quiet contradiction embedded within the fabric of observation. This is where the shift begins to take shape, because a single irregularity does not change science, but it plants a seed. It introduces doubt into a system that relies on consistency, and once that doubt exists, it cannot be ignored. It forces a question that echoes beneath every subsequent observation. What if this is not an error? Imagine the moment when that question becomes unavoidable, when the data has been checked and rechecked, when every known explanation has been exhausted, and the anomaly remains exactly where it was, untouched by every attempt to remove it. That is the moment where reality begins to feel less stable, not because it is collapsing, but because it is revealing something that was never accounted for. And then, it happens again. Another irregularity, similar but not identical, close enough to suggest a connection, different enough to resist immediate classification. Now the anomaly is no longer isolated. It is becoming a pattern, but not one that fits within existing models. It is a pattern without a category, a signal without a source, a behavior without a rule. This is the first true fracture in certainty. Because once a pattern emerges, the mind can no longer dismiss it as coincidence. It demands attention. It demands explanation. And when no explanation is available, it creates a tension that cannot be resolved through familiar methods. The tools still work. The data is still accurate. But the meaning behind it begins to slip beyond reach. This is what a glitch in reality feels like. Not a dramatic collapse of understanding, but a quiet misalignment that grows with every observation. A sense that something is present that should not be there, and yet refuses to leave. It does not announce itself as a discovery. It reveals itself slowly, forcing those who observe it to confront the limits of what they know. And once that limit is reached, there is no way back. Because the moment you accept that something exists beyond your current understanding, you are no longer standing on certainty. You are standing on the edge of something new, something that may redefine the rules you once trusted without question. The anomaly was no longer just a detail in the data. It was becoming a doorway. The pattern no one wanted to see. At first, it was easier to believe there was no pattern at all. Randomness is comfortable. It allows anomalies to exist without consequence, to be acknowledged without forcing change. If the signals were chaotic, if they followed no structure, then they could remain an unresolved curiosity, something to revisit later. But the universe does not always offer that kind of comfort, because the signals kept coming. not in a steady rhythm, not in a way that could be predicted with a simple equation, but with a consistency that felt deliberate. Intervals began to emerge, subtle repetitions hidden beneath irregular timing, energy levels that shifted yet stayed within a narrow range. It was not obvious at first. It required patience, comparison, and a willingness to look deeper than surface-level noise. But once the pattern began to reveal itself, it became impossible to ignore. And that is when the tension changed, because a pattern means structure, and structure implies a process. Something is generating these signals, something that operates according to rules we do not yet understand. This is where the discomfort begins to grow, not because the phenomenon is dangerous, but because it is coherent in a way that challenges everything we thought we knew about that region of space. Imagine watching something that behaves with intention, but without explanation. The data was mapped, overlaid, analyzed across different timeframes. Independent observatories confirmed the same sequences. The variations were not errors, they were part of the behavior. Each new detection added another layer, another piece of a structure that seemed to exist just beyond the reach of current theory. It was no longer a question of whether there was a pattern. The real question was why it existed at all, and that question did not have a comfortable answer. Because if the signals followed known astrophysical processes, they would already be classified. If they were produced by extreme objects like neutron stars or black holes, their signatures would align with what we have observed countless times before. But they did not. They occupied a space between the known and the impossible, familiar enough to be measured, foreign enough to remain unexplained. This is where resistance appears. The human mind, even in science, seeks stability. It tries to protect the frameworks that have proven reliable, so the pattern was tested against every model available. Simulations were run, variables were adjusted, hypotheses were stretched to their limits in an attempt to contain what was being observed. But each attempt led back to the same conclusion. The pattern was real, and it did not belong to any known category. Now, consider what that means. A repeating phenomenon in the universe, governed by structure, yet existing outside our understanding. It suggests that the rules we rely on may not be as complete as we believed, that there are mechanisms at work that we have not yet discovered, processes unfolding in regions we thought were already understood. It introduces a possibility that is both unsettling and extraordinary, the possibility that the universe is operating on layers we have not yet learned to see. And once that idea takes hold, it changes everything. Because the pattern is no longer just a feature of the data. It becomes a signal in a deeper sense, not just something being detected, but something revealing the limits of our perception. A reminder that what we observe is only a fraction of what exists. The pattern was never meant to be found easily. It had to be uncovered, piece by piece, through persistence and doubt. And now that it has been seen, it cannot be unseen. It forces a shift from observation to confrontation, a confrontation with the unknown, with the incomplete, with the possibility that the universe still holds structures far beyond our current reach. And if this pattern exists, then the next question becomes unavoidable. What else is hidden in the data, waiting for us to recognize it? Instruments begin to disagree with reality. The first signs of conflict did not come from theory. They came from the instruments themselves. Devices built to measure the universe with extraordinary precision began to produce results that did not align with expectation. Not slightly off, not within acceptable margins of error, but fundamentally inconsistent with the models they were designed to confirm. At first, the suspicion fell on the tools. Calibration was checked, systems were reset, external interference was considered. Because when instruments disagree with reality, the natural assumption is that something has gone wrong in the process of measurement. Science depends on reliability, and these systems had proven themselves countless times before. They had mapped distant galaxies, captured the echoes of cosmic events billions of years old, and delivered data that matched theory with remarkable accuracy. But now, they were telling a different story. Independent observatories, separated by vast distances on Earth and beyond, began to detect the same anomaly. Different technologies, different methodologies, yet the same result appeared again and again. The signal was not an illusion created by a single instrument. It was being observed across multiple systems, each confirming the existence of something that should not behave the way it does. This is where certainty begins to fracture, because when one instrument fails, it can be dismissed. When many instruments agree on something that contradicts theory, the problem is no longer technical. It becomes conceptual. It suggests that the tools are working exactly as intended, and that what they are detecting is real. And if it is real, then the models used to interpret that data may be incomplete. Imagine looking at a map that has guided you perfectly for years, only to find that every compass you use suddenly points in a direction the map does not recognize. This is the moment scientists found themselves in. The data showed variations in energy that did not match any known emission process. The timing of the signals conflicted with the expected behavior of known cosmic objects. Even the spatial origin of the phenomenon appeared unstable, as if the source itself was not fixed in a way that could be easily defined. It was not just a matter of unusual readings. It was a systematic disagreement between observation and expectation. And that disagreement could not be ignored, because science does not move forward by protecting its models. It evolves by confronting their limitations. Each contradiction is an opportunity, but also a challenge. It forces a reevaluation of assumptions that were once considered solid. It requires a willingness to question not just what is being observed, but how it is being interpreted. This is where the tension deepens. Because if the instruments are correct, then reality is behaving in a way that current theory cannot explain. And if reality itself is not aligning with our understanding, then the gap between knowledge and truth becomes impossible to overlook. It is no longer a question of refining equations or adjusting variables. It becomes a question of whether something fundamental has been missed. The instruments did not fail. They revealed. They revealed that the universe is capable of producing signals that exist outside the boundaries of our expectations. They revealed that our methods of observation, as advanced as they are, may still be interpreting only a fraction of what is truly happening. And most importantly, they revealed that the phenomenon we are observing is not just unusual, it is incompatible with what we thought was real. This is the kind of moment that reshapes science, not through gradual improvement, but through confrontation. A direct encounter with something that cannot be explained within the current system. And once that encounter happens, the path forward is no longer clear. It becomes uncertain, open, and filled with possibilities that extend far beyond the familiar. Because if our instruments are telling the truth, then the universe is not just more complex than we imagined. It is more complex than we are currently able to understand. And that realization leads to a turning point. Observation is no longer enough. Something deeper has to begin. The moment observation became obsession, there is a threshold in science where curiosity is no longer enough, a point where observation transforms into something more urgent, more focused, almost impossible to step away from. That threshold was crossed the moment the anomaly refused to fade into the background and instead grew sharper, more consistent, more present with every passing observation. What began as a curiosity became a priority. Telescopes that once followed scheduled surveys were redirected. Time that had been allocated to other projects was reassigned. Research teams across continents began to communicate more frequently, sharing data, comparing results, trying to understand whether what they were seeing was truly happening, or if they were all being drawn into the same illusion. But the illusion never collapsed. It only became more defined, and that is when attention turned into fixation. Because the phenomenon was no longer passive, it was evolving. The signals were not repeating in a static way. They were shifting, adapting in subtle but undeniable patterns. Timing intervals narrowed, then expanded. Energy levels fluctuated within ranges that hinted at an underlying mechanism, something structured yet elusive. It was not chaotic. It was not stable. It existed somewhere in between, and that in-between space is where the most difficult questions emerge. Imagine watching something that feels like it is responding to being observed. That thought alone was enough to unsettle even the most grounded interpretations. Not because there was evidence of intention, but because the behavior resisted every attempt to be reduced to a simple, natural process. The more data that was collected, the more it seemed that observation itself was revealing layers that had not been visible before, as if the phenomenon required sustained attention to fully emerge. Global networks of observatories began to coordinate. Signals were tracked across different wavelengths, from radio to high-energy emissions, each revealing a slightly different aspect of the same event. Satellites joined the effort, offering perspectives free from atmospheric distortion. Algorithms were developed to detect even the faintest recurrence, scanning vast data sets in search of patterns too subtle for the human eye. What had once been a single anomaly was now a continuous stream of investigation, and still, no explanation held. Theories were proposed, tested, and set aside. Each one captured part of the behavior, but none could account for the whole. It was as if the phenomenon existed just beyond the reach of every model, revealing enough to challenge understanding, but never enough to be fully contained by it. This is the space where obsession thrives, not because of certainty, but because of the absence of it. Sleep became secondary to analysis. Time blurred into sequences of observation, interpretation, and reevaluation. The phenomenon was no longer something that could be approached casually. It demanded attention, it demanded presence. And for those studying it, it began to feel less like a distant event in space and more like a problem that had to be solved, no matter how long it took. But something unexpected happened in that process. The more intensely it was studied, the more it revealed inconsistencies that could not be ignored. Not just in the phenomenon itself, but in the frameworks used to understand it. Assumptions that had once felt secure began to weaken. Connections that once seemed obvious started to dissolve. It was not just the anomaly that was changing, it was the perspective of those observing it. This is where science enters a different state. A state where the goal is no longer just to explain what is seen, but to question how it is seen. To reconsider the tools, the models, the very language used to describe reality. Because when observation becomes obsession, it strips away comfort. It removes the distance between the observer and the unknown, and in that proximity, something becomes clear. The phenomenon is not just something to be measured. It is something that is forcing a transformation in the way we understand the universe itself. And that transformation is only just beginning. Data that breaks the laws of physics. There comes a moment in every deep investigation when the data stops behaving like information and starts behaving like a contradiction. That moment arrived quietly, not with a single shocking result, but with a series of measurements that refused to align with the very laws that had defined modern physics for over a century. At first, the deviations seemed small, energy outputs that did not scale the way they should, timing intervals that drifted outside expected limits, emission signatures that suggested processes no known object could sustain. Each inconsistency, taken alone, could be explained away. Instruments have margins of error. Natural systems can behave unpredictably under extreme conditions. But when these inconsistencies began to overlap, to reinforce each other across multiple observations, they formed something much harder to dismiss: a pattern of impossibility. The phenomenon was producing bursts of energy that appeared to exceed theoretical constraints. Not by a slight margin, but in ways that forced scientists to reconsider the assumptions behind those constraints. According to established models, such emissions would require conditions that could not exist without collapsing into something entirely different. And yet, the data showed no sign of collapse, no transition into a known state. It continued, stable within its own contradiction. This is where the ground begins to shift. Because physics is not just a collection of ideas, it is a framework built on principles that have been tested repeatedly across time and space. Among those principles are limits, boundaries that define what can and cannot happen, the speed at which information can travel, the way energy is conserved, the relationship between mass, space, and time. These are not suggestions. They are the foundation of how we interpret reality. And now the data was challenging that foundation. Some of the signals appeared to compress intervals in a way that suggested information was arriving faster than expected. Not in a way that could be easily measured as a violation, but in a way that hinted at something deeper, as if the path the signal traveled was not as straightforward as previously assumed, as if space itself might not be behaving uniformly in the region where the phenomenon originated. Other measurements revealed energy distributions that did not decay in the expected manner. Instead of dissipating predictably, the signal retained coherence over distances that should have weakened it beyond detection. It was as though the energy was being sustained by a mechanism that current physics does not account for, a process hidden beneath the observable layer, influencing outcomes without revealing its structure. This is where familiar explanations begin to fail. Scientists turned to extreme models, exploring scenarios involving exotic states of matter, unusual gravitational effects, and interactions that push the limits of known theory. Some proposed that the phenomenon might be interacting with regions of space where the rules behave differently, where the fabric of reality is distorted in ways that are not yet fully understood. Others suggested that what we are observing is not a violation, but a glimpse of a deeper layer of physics that has always been there, waiting to be uncovered. But no single explanation held. Each theory illuminated part of the behavior, but left other aspects unresolved. It was like trying to describe a shape that changes depending on how you look at it. Every angle revealed something new, but never the complete picture. And in that incomplete picture, a realization began to take form. The laws of physics were not being broken, they were being challenged. And there is a difference. Because when something breaks a law, it implies an error in observation. But when something challenges a law, it suggests that the law itself may not be the full story. That there are conditions, environments, or scales at which the rules we rely on begin to transform into something more complex. This is the edge of understanding, a place where certainty gives way to possibility, where the universe stops confirming what we know and starts revealing what we do not. And in that space, every new piece of data becomes more than just information. It becomes a clue, pointing toward a reality that is larger, deeper, and far less constrained than we once believed. The data is not just telling us that something unusual is happening. It is telling us that the boundaries of our knowledge are closer than we thought. And beyond those boundaries, something entirely new may be waiting. The hidden variable. No one accounted for. At some point, every investigation reaches a limit where adding more data no longer clarifies the picture. It complicates it. The anomaly had been observed, measured, compared, and challenged from every possible angle. And yet, something essential was still missing. Not in the instruments, not in the calculations, but in the assumptions themselves. Because every model begins with what we believe to be true. Physics does not just describe reality, it filters it. It selects variables that matter and discards those that seem irrelevant. Mass, energy, time, distance. These are the pillars we use to construct meaning from observation. But what if something exists outside those pillars, something that influences outcomes without being directly measurable within the framework we rely on? That is when the idea of a hidden variable begins to take shape, not as speculation, but as necessity. The behavior of the phenomenon could not be fully explained by any combination of known forces or interactions. Each attempt to model it left behind inconsistencies that could not be resolved by adjusting existing parameters. It was as if an unseen factor was shaping the results, guiding the signal in ways that could not be accounted for by the variables we were using. Imagine solving an equation where every number is correct, every operation is precise, and yet the result is always wrong. Not slightly off, but fundamentally misaligned. That is what the data began to feel like. So the focus shifted. Instead of trying to force the phenomenon into existing models, scientists began to question the models themselves. What if there is something influencing space that we cannot detect directly? Something that does not emit light, does not interact in conventional ways, yet still leaves an imprint on the behavior of energy and motion. This is not an unfamiliar concept. We have already encountered hints of unseen influences in the universe, effects that suggest the presence of something beyond direct observation. But what is happening here feels different, more immediate, more precise. The anomaly is not just being affected by something hidden. It appears to be interacting with it in a structured way, and that changes everything. Because a hidden variable is not just an unknown, it is a missing piece of reality, a component that, once understood, could redefine how we interpret everything from the smallest particles to the largest cosmic structures. It suggests that what we perceive as complete may only be a surface layer, a simplified version of a deeper system operating beneath it. Now, consider the implications. If this hidden factor exists, then it has always existed. It has been present in every observation, every equation, every conclusion we have drawn about the universe. The difference is that, until now, its effects were either too subtle or too diffuse to be recognized. But this phenomenon has brought it into focus, concentrated its influence into something we can no longer ignore. This is where the boundaries of knowledge begin to dissolve. Because once you accept that something fundamental is missing, every certainty becomes provisional. Every law becomes a stepping stone rather than a final answer. The universe is no longer a closed system waiting to be fully decoded. It becomes an open question, one that expands with every attempt to define it. And yet, this is not a step backward. It is an invitation to look beyond what is visible, to consider that reality may operate on layers we have not yet learned to access. Layers where familiar rules are part of a larger structure, where cause and effect are influenced by variables we have yet to name. The anomaly is not just revealing a hidden variable, it is pointing toward a hidden dimension of understanding. And once that direction is clear, the next step becomes inevitable. Because if something unseen is shaping what we observe, then the theories we build to explain it must evolve beyond anything we have imagined before, competing theories on the edge of imagination. Once it became clear that no existing model could fully contain what was being observed, the response was inevitable. Theories began to emerge, not cautious adjustments to known ideas, but bold attempts to step beyond them. Each one was an effort to bridge the gap between what the data revealed and what our understanding could currently support. At first, the proposals stayed close to familiar ground. Some suggested extreme versions of known phenomena, unusual configurations of neutron stars, rare interactions between black holes, environments where gravity and energy might behave in ways we had not yet observed. These explanations stretched existing physics to its limits, testing whether the anomaly could still be contained within the boundaries of what we already accept as real. But the anomaly resisted. Every model that tried to explain it using known mechanisms left something unresolved, a detail that did not fit, a behavior that could not be reproduced. And so the theories began to move further outward, into territory that felt less certain, but more capable of capturing the full complexity of what was unfolding. This is where imagination enters science in its most disciplined form, not as fantasy, but as a tool for exploring possibilities that have not yet been proven. Scientists began to consider the existence of processes that operate beyond our current detection methods, interactions between fields we do not yet understand, regions of space where the structure of reality itself may differ from what we experience locally. Some theories propose that the phenomenon might be linked to distortions in the fabric of space, areas where geometry behaves in ways that alter the path and nature of energy. Others suggested that we could be observing the effects of a deeper layer of physics, one that only becomes visible under specific conditions, when multiple variables align in a precise and rare configuration. And then there were ideas that pushed even further, possibilities that challenged not just specific laws, but the framework of interpretation itself. What if the signal is not being generated in the way we assume? What if the concept of a single source is too limited to describe what is happening? What if the phenomenon is not local, but distributed across space in a way that makes it appear as a single event from our perspective? These questions do not provide answers. They expand the space in which answers might exist. And that expansion is both necessary and unsettling, because the further these theories move from established ground, the more they demand a shift in how we think, not just about the anomaly, but about the nature of reality itself. They require us to accept that our current models may be approximations, useful within certain limits, but incomplete when faced with phenomena that exist beyond those limits. This is the edge of imagination in science, a place where ideas are not yet confirmed, but are grounded in the need to explain what has been observed. Each theory competes not just for acceptance, but for coherence. It must align with the data, account for the inconsistencies, and remain internally consistent while reaching beyond the known. So far, none have succeeded completely. But that is not failure, it is progress, because each attempt reveals something new. Each theory, even when incomplete, highlights aspects of the phenomenon that demand attention. It refines the questions, sharpens the focus, and moves us closer to a framework that might one day hold everything together. What matters now is not which theory is correct. What matters is that the anomaly has forced us to think differently, to explore ideas that once seemed unnecessary, to consider structures of reality that extend beyond our current reach. And in doing so, it has opened a space where discovery is no longer limited by what we already know. Theories will continue to evolve, but the phenomenon remains, waiting, unresolved, challenging every idea we place in front of it, a universe more alive than we thought. There is a subtle shift that happens when the unknown refuses to be reduced to a problem. It stops being something to solve and starts becoming something to experience. That shift is happening now, because the phenomenon we have been following is no longer just an anomaly in the data. It is beginning to reshape the way we perceive the universe itself. For a long time, we have described the cosmos as a system, a vast, elegant structure governed by laws that operate with precision and consistency. Stars are born, evolve, and die. Galaxies collide and merge. Energy moves, transforms, and dissipates. Even in its most violent moments, the universe follows patterns that can be understood, predicted, and described. It is a system that feels stable, even when it is dynamic. But what if that description is incomplete? What if the universe is not just a system, but something more responsive, more layered, more capable of behaviors that cannot be fully captured by static rules? The phenomenon we are observing suggests exactly that. It behaves in ways that feel less like a fixed process and more like an unfolding interaction. Not random, not chaotic, but not entirely bound by the rigid predictability we have come to expect. This is where perception begins to evolve, because when you observe something that adapts, that shifts, that reveals different aspects depending on how it is studied, you begin to question whether the universe is as passive as we once believed. Not alive in the biological sense, but active in a way that suggests complexity beyond simple cause and effect, a kind of depth that cannot be fully mapped from a single perspective. Imagine a reality that does not just exist, but expresses itself, a reality where what we observe is only a surface layer, and beneath it lies a network of interactions that we are only beginning to glimpse. The anomaly feels like a window into that deeper layer, a moment where the universe reveals behavior that does not fit into our simplified descriptions, but instead hints at a richness that extends far beyond them. This does not mean the laws of physics are wrong. It means they may be part of something larger, part of a framework that operates differently depending on scale, context, or conditions we have not yet learned to identify. The universe may not be breaking its rules. It may be showing us that the rules themselves are more flexible, more intricate, and more interconnected than we assumed. And that realization carries weight, because it changes the relationship between observer and reality. It removes the illusion that we are standing outside the system, looking in with complete clarity. Instead, it places us within a process that is still unfolding, still revealing, still beyond full comprehension. The more we observe, the more we realize that observation itself is part of the experience. This is not a loss of understanding, it is an expansion of it, a movement from certainty to awareness, from control to curiosity, from the idea that we can fully define the universe to the recognition that we are participants in something far more complex than any single model can capture. The anomaly has not just introduced a new question, it has introduced a new way of seeing, a way that embraces uncertainty, not as a limitation, but as an invitation to explore deeper layers of reality. A way that recognizes that what we do not know is not empty space, but a field of possibilities waiting to be understood. The universe is not becoming more mysterious. We are becoming more aware of its depth, and that awareness leads to something inevitable, a need to understand what this means for us, what this means for humanity's place in the cosmos. There is a moment, after the data has been analyzed and the theories have been stretched to their limits, when the question shifts direction. It stops being only about the phenomenon and begins to reflect back on us. Because every discovery in the universe, no matter how distant, eventually leads to a deeper question. What does this mean for our place within it? For a long time, humanity has stood on a fragile balance between certainty and wonder. We have learned to measure the cosmos with precision, to calculate distances that stretch across billions of light years, to describe processes that unfold over timescales far beyond human experience. And in doing so, we have built a narrative where we are observers, small but capable, positioned within a universe that can be understood through reason and exploration. But now, that narrative is being challenged, not by something that replaces it, but by something that expands it beyond its current limits. The phenomenon we have been following does not simply introduce a new object or a new category. It introduces a gap, a space between what we know and what we can explain. And that space is where perspective begins to change. Because if the universe contains structures, processes, or variables that exist beyond our current understanding, then our role as observers becomes more complex. We are no longer just discovering reality. We are encountering its boundaries. And those boundaries are not fixed. They move as we move, expand as we expand, revealing more the deeper we look. Imagine standing at the edge of an ocean at night. You can see the surface, feel the movement of the waves, sense the vastness stretching beyond the horizon. But you also know that beneath that surface lies a depth you cannot fully perceive. Entire systems, interactions, and forms of existence that remain hidden, not because they are unreachable, but because they require new ways of seeing. This is where we are now. The anomaly has shown us that the universe is not just something to be mapped, it is something to be approached with humility. Because every time we believe we have reached a point of clarity, something emerges that reminds us how much remains beyond our grasp. And that reminder is not a limitation. It is a form of guidance. It tells us that knowledge is not a destination. It is a process, a continuous unfolding that does not end with answers, but evolves through deeper questions. And in that process, our place in the cosmos becomes something dynamic, not fixed, not defined by what we already know, but shaped by our willingness to explore what we do not. This is the perspective that transforms science into something more than analysis. It becomes a dialogue, a conversation between humanity and the universe, where each discovery is both a response and an invitation. We observe, the universe reveals. We question, the universe expands the question. And in that exchange, we begin to understand that we are not separate from what we are studying. We are part of it, made of the same elements, governed by the same principles, yet capable of reflecting on the system from within. That is what makes this moment so significant. Not just because of the anomaly itself, but because of what it reveals about the nature of understanding. We are not at the center of the universe, but we are at the center of a perspective that is still growing. And that perspective is about to be tested in a way we have never experienced before. Because the final question is no longer about what we have found. It is about what we are willing to accept. The question that changes everything. There is always a final moment in every great discovery. Not the moment when the answer is found, but the moment when the right question is finally revealed. And that is where we are now. Because after all the data, all the analysis, all the theories pushed to their limits, the phenomenon has left us with something far more powerful than an explanation. It has left us with a question we cannot ignore. What if the universe is not bound by the limits we believed defined it? Not in the sense that laws are broken, but in the sense that what we call laws are only a fraction of a deeper structure. A structure that reveals itself only under certain conditions, only when observation reaches a level of precision and persistence, capable of exposing what usually remains hidden. The signal, the pattern, the contradictions in the data, all of it points in the same direction. There is more than our current models can describe, more than our instruments can fully interpret, more than our assumptions are prepared to accept. And yet, it is there, present within the very data we have collected, waiting to be understood not by forcing it into old frameworks, but by allowing those frameworks to evolve. This is the turning point. Because science advances in two ways, by confirming what we expect and by confronting what we do not. The first builds confidence. The second transforms understanding. And transformation is rarely comfortable. It requires letting go of certainty, stepping into uncertainty, and trusting that what lies beyond will lead to something deeper, not something less. Now imagine what this means going forward. Every new observation will carry a different weight. Every signal will be examined not just for what it confirms, but for what it challenges. The anomaly is no longer an isolated mystery. It is a lens, a way of looking at the universe that prioritizes what does not fit, what resists explanation, what forces us to expand the boundaries of thought. And that lens will change how we see everything. Because once you accept that reality may be layered beyond your current perception, you begin to question the completeness of every conclusion. Not to reject knowledge, but to refine it, to push it further, to recognize that understanding is not about reaching an endpoint, but about continuously moving towards something that becomes more complex the closer you get. This is not the end of the story. It is the beginning of a deeper one. The phenomenon is still being observed. The signals are still being recorded. The data continues to grow, revealing new variations, new details, new inconsistencies that refuse to settle into a final explanation. And that is precisely what makes this moment so important. Because we are not looking at something that has already been understood. We are looking at something that is still unfolding. Right now, in real time, somewhere in the vast expanse of space, beyond the limits of what we can see directly, this phenomenon continues to exist, to evolve, to challenge everything we think we know. And with every new piece of data, it brings us closer to a realization that may redefine not just physics, but our entire relationship with reality. So the question remains, not what is it, but what does it mean for everything else we have yet to discover? Because whatever the answer is, it will not just explain the anomaly, it will change the way we understand the universe itself.